So let's talk about how we actually verify inverse functions using equations. So I have two functions graphed here, right? So this one will let be f of x, and this one I've graphed as the inverse. So it's f inverse of x, right? And we've looked at these before, right? And there's this nice dividing line. That's the reflection line right down the middle, and that's the line y equals x. So we know graphically two functions are inverses if they are perfect reflections of each other over that line y equals x. And that makes sense because when we find inverse functions, we're flipping the x and y coordinates so that y equals x line should be the middle. So we can actually, without looking at a graph, which is especially great if we have more complicated functions and we don't want to make a graph for them, we can actually use the equations to verify, to check if two functions are inverses of each other. So we have this rule in math that says if two functions we'll call them f of x and g of x. Right, so I'm actually going to relabel this one as g of x just kind of to match the definition. Are inverses of each other. Then the following two statements have to be true. We know that f of g of x will equal x, and the opposite is also going to be true. G of f of x will also equal x. So, right, that's function composition notation. So function composition can be used to check if two equations are inverse functions of each other. And normally when we do function composition, right, the order really matters because if we do one function on the outside and one function on the inside, the answer to that is very different normally if we flip the order. But if they're inverses of each other, they actually cancel out and give us back this y equals x line. So it makes sense that they should equal out to the x line because that's their reflection line. That's the middle point of those two graphs. So if we put the equations together, everything should end up on that reflection line. So I'm going to show you two examples. So we're going to use function composition to check if these two groups of functions are inverses of each other. So we're going to use function composition to verify if f and g, my pencil does not want to work, and g of x are inverses. So an example, I guess I'll call this example A. We're going to let f of x equal negative 1/2 x minus 3/2. And we'll let g of x equal negative 2x minus 3. So we need to check both directions. So we're going to be doing some function composition. So I'm going to put f on the outside first. I'm going to do f of g of x first. So that means that everywhere I see an x in my f function, I'm going to replace that with g. So I'm just going to draw my function structure. So 1/2 times whatever minus 3/2. And then I'm going to plug the g function into the inside. So negative 2x minus 3. So then the next step would be to distribute. So negative 1/2 times negative 2, well, that's going to make a positive, and 1/2 of 2 is 1, so I'm going to get 1x. And then negative 1/2 times negative 3 is positive, and that's going to be 3 over 2 minus 3 over 2. So these are going to cancel each other out, and we're going to be left with x. So f of g of x is equal to x. Okay, so this direction works. But we have to check both directions because sometimes one direction could equal x, but the other direction doesn't. So we need to check both of them. So now we're just going to flip the order and we're going to do g of f of x. So I'm just going to set up my structure, right? So I see an x here in the g function. So I'm going to do -2 times whatever I plug in minus 3. And I'm going to plug in my f function. So -1/2 x minus 3/2. So again, I'm going to distribute my -2. So I have -2 times -1/2, that's positive 1x. That's going to be, so -2 times -3/2, right? So if we go off to the side just to kind of do that, that's -2/1 times -3/2. That's, if we go straight across, right, that's positive 6/2. It's going to give me 3. So plus 3 there, and then I have this minus 3 on the end. So then 3 minus 3 is going to cancel out. And again, we're just left with 1x, or just x. So that direction works too. So because both directions work like that, we can say that f of x and g of x are inverses. Okay, so let's do one more example. We'll call this example B. So for here, let's let f of x equal 3x minus 9 all over 5, and we'll let g of x equal 4/3 x plus 8/3. So the first direction I'm going to check is f of g of x. So I see an x here in my f function, so I'm just going to go ahead and draw my structure in. So 3 times whatever I plug in minus 9 all over 5. So I'm going to plug in my g function. So I'm going to distribute my 3 through that group. Now, when I distribute 3 through both of those fractions have a 3 in the denominator, so that really means I'm dividing both of those numbers by 3. So when I multiply by 3, the 3's are all going to cancel out actually. And we're going to be left with 4x plus 8 minus 9 all over 5. And if I combine my like terms, it's going to be 4x minus 1 over 5. And then I can't go any further than that, right? And this does not equal x, right? So since it doesn't simplify down to x, we already know that f of x and g of x are not inverses. Right? So if they're not inverses, as soon as one direction doesn't work, you know that they're not inverses because you need both directions to work. But if one direction works, then you need to check the other direction. So I'm going to write 2 problems on the screen for you to try by yourself. So you're going to do the same thing. You're going to verify both functions. So for OYO 1, right, we're going to let f of x be equal to 5x over 4 and g of x be equal to 20 plus 3x all over 5. And then for OYO 2, I want you to check to see if f of x equaling 1/6 x minus 11/3 and g of x equaling 6x plus 22, if those are inverses. So go ahead and try both of those. So I'm going to quick go through my work to show you how you would do these, just so you can check your work. So I'm going to do f of g of x first. So for that, I can see that I have an x here. And what I can actually do here is I can write that as 5/4 times x and put the x off to the side. So that's what I'm going to do here. So I'm going to write 5/4 times whatever I plug in, and then I'm going to plug in my g function. So I have a 5 in the numerator and a 5 in the denominator, and I'm multiplying, so I can cancel those out. And then I would be left 20 plus 3x all over 4. And there's nowhere else to go from here, and this does not equal x. So these are not inverses. So then let's go ahead and check in OU number 2 if they're inverses. So we have f of g of x So I have an x here next to my 1/6. I'm going to do 1/6 times whatever I plug in, minus 11/3. And I'm plugging in the g function, which is 6x plus 22. So 1/6 of 6x is 1, so I get 1x plus 22 over 6 minus 11/3. And then I can reduce 22 over 6 by 2. So now I have x plus 11 over 3 minus 11 over 3, and those two are going to cancel out, and I'm going to be equal to x. Right, so that direction works. And so I got to check the other direction just to make sure that both are good. So now I'm going to do g of f of x. So I'm going to do 6 times whatever plus 22 because my x is right there next to the 6. And I'm going to plug in my 1/6 x minus 11/3. So 6 times 1/6, right, if I distribute through, it's going to be 1x minus 6 times 11 is 66 over 3 plus 22. Now 66 over 3, that divides to be 22. So then my 22s are going to cancel out. And again, we're just left with 1x. So these are inverses.